Hello, we're going to work on Module 4 Investigation 1, the meaning of exponents. For exercises 1 through 4, Hannah, Christy, and Jolene discover a secret that no one else knows. On day 1, each of them tells 2 other people. After that, everyone who learns their secret on a given day tells the secret to 2 new people the next day. The pattern continued for 15 days. Determine how many people learned the secret on day 2. Explain why this makes sense. We can clearly see from the diagram that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 people who learned the secret on day 2. But we need to explain why this makes sense. If you think about it, each day the number of people who knows the secret doubles because we're always telling 2 people. So if I told the secret to 2 people, that's doubling right there, 1 to 2. And so if each of these 3 original people tell the secret to 2 people, then we'll double and we'll get 6 people who know the secret. Then if all 6 of those people tell 2 new people, we'll double again to get 12 people. It says that from the diagram above, we see that 12 people learned the secret on day 2. We will represent the number of people who learned the secret on a given day in 3 different formats that will help us generalize the mathematics. Decimal notation is what we usually use. 12 people. Product notation just means factoring the number 12 into its usually prime numbers. So here we have 3 times 2 times 2 people. And then the exponential notation means we take that product 2 times 2 and we write 2 squared. So it's really interesting, this 3, if you think about it, that's the number of people we started out with originally. And then each day we add another factor of 2. Day 1, 3 times 2 is 6. Day 2, 3 times 2 times another 2 makes 12. Number 2, let x equal the day number and y the number of people who learned the secret on day x. Fill in the following table. Okay, so we have the day numbers here, and it looks like all of those are already filled in for us. And we already have all our decimal notation. Let's see, notice day 0 is not there, but that's okay. So we have 6 people, and then it doubles each time. And then we have just the product notation, and the exponential notation is left blank. So let's do the product notation. Right here, 24, that's the 3rd day. We can look at this pattern here. On the first day, the number of people who learned the secret was 3 times 2. On the second day, it was 3 times 2 times another 2. So then on the 3rd day, it'll be 3 times 2 times 2 times 2. I notice a pattern here that on the first day there's 1 2, on the second day there's 2 2s, on the 3rd day there's 3 2s, on the 4th day there's 4 2s, on the 5th day there will be 5, and then on the 15th day it'll be 15 2s multiplied by 3. So you could write it out like in the full product notation, or we could just abbreviate, do something like this to let us know that we have 15 factors of 2 there. Okay, so exponential notation's kind of simpler. 3 times 2, we only have 1 2, so this is 3 times 2 to the 1st. 3 times 2 times 2 is 3 times 2 squared. 3 times 2 times 2 times 2, we have 3 2s, that's 3 times 2 cubed. This one's done for us. Here we have 3 times 2 to the 5th. Notice that the exponent is just the number, it's just the day, so I know that the 15th will be 3 times 2 to the 15th. And we call, like I said, this the exponent, and this is our factor, or the base. Number 3a, what quantities are varying in the secret sharing problem? So if I think about the quantities that are varying, the day, that's a number, it's changing, the number of days is increasing, and the number of people who know the secrets is also increasing. It might be helpful to think about the number of people who know the secret on a particular day. We could also think about the total number of people, but like with our table here, what was really important is the number of people who learned the secret on the particular day, which we have in this column here, rather than just the total number of people. We need to be specific. Part B, if you were to describe to your friend how the number of people who learned the secret on a given day is growing, what would you say? Well, I would say that the number of people is doubling each day. Number 4a, define a function f that determines the number of people p who learned the secret on day n. So we want a function f, and we want that function f to determine the number of people p. So we're determining the number of people p. So p is going to be the output of the function f, and f is going to be in terms of n, the number of, or actually the day. And so what would that function look like? Let's go back to the table. Notice here in this last column we have the output, or the number of people who learned the secret on day x, and it's always 3 times 2 to the first, 3 times 2 squared. It's always 3 times 2, and then the exponent is just the particular day. So basically the function is y equals 3 times 2 to the x, or in our case with our variable n, y equals 3 times 2n, or f of n equals 3 times 2n. Notice we could check our function to make sure it works. On the first day, we have 6 people. On the second day, we have 12, and so on. Part B. Use the function defined in Part A to determine the number of people who learned the secret on day 12. So our day is 12. I would recommend just plugging that into the calculator, and we get a huge number. 12,288 people would know the secret on day 12. So this is a key characteristic of exponential growth. Notice that we have n, our variable, our input is the exponent. And when we have exponential growth, things grow really quickly. 5a. Now we will consider a slightly different situation. Suppose that 4 people initially knew the secret, and on day 1 they each tell 5 people. Everyone who learns the secret on a given day tells the secret to 5 new people the next day. Modify the function you created in exercise 7 to reflect this change. I don't know what it means by exercise 7 there. I'm guessing we can just modify our function f of n equals 3 times 2 to the n. Remember that the 3 was the number of people who first knew the secret. And this 2 was the number of people that they tell the secret to each day. So now, initially we're going to have 4 people, so we'll just put a 4 in place of that 3, and then they're each going to tell 5 people, so our function will look like this. Part B, modify the function you created in Part A to determine the number of people who learned the secret on the nth day. If K people initially knew the secret on day 1, they each tell B people. Then everyone who learns the secret on a given day tells the secret to B new people the next day. Okay, so now instead of, let's see, 4 or 3 people initially knowing the secret, we have K people initially knowing the secret. So here K is a constant, it's not varying. And then there were they told B people each day. So that's our base here, B to the n. And here the only variable is the n. K and B are both particular numbers. Number 6. Suppose that 5 people initially discovered the secret, and we want to call this day 1. Then, on day 2, each of these 5 people tell 3 new people the secret. This pattern continues so that anyone who learns the secret on a given day tells 3 new people the next day. Define a function that determines the number of people P who learned the secret on day N. Hint, it may help to create a table of values. Okay, let's create a table. So I've made a bit of a table here. This column is the day, and here in this column we have people who learned the secret. On day 1 we have 5 people who already knew the secret, and then they each told 3 people, so 5 times 3 would be 15 people who learned the secret on day 2. Then on day 3, those 15 people tell 3 more, so we have 45, and then on the 4th day, all these people that already know the secret tell 3 more, so we have 135. If we want to define a function, we need to translate this product notation into exponential notation. Now in the previous problem, the exponent was the day, but take a look here. Each time, like here we have 1 factor of 3, but the day is 2. Then on day 3 we have 2 factors of 3, and on day 4 we have 3 factors of 3. Instead of having 5 times 3 to the n, notice that we're actually 1 behind. Here on the 2nd day there's only 1 factor of n. On the 3rd day there's only 2 factors of n. On the 4th day there's only 3. So we have to take away 1. So I shouldn't have used n there. This is really 2 minus 1. This one is 5 times 3. 3 minus 1 is square. This one's 5 times 3 to the 4 minus 1. So in general, our function f of n equals 5 times 3n minus 1. Number 7, simplify the following expressions and write the final result using only positive exponents. You've probably all done something like this in high school. We're going to be drawing on lots of exponential theorems from high school. Let me first just give you the answers for each of these, and if you have them, great, you know how to do them, just move on, and then I'm going to take some time to explain them. Part A, 72x to the 8th. Part B, a to the 13th, b to the 15th. Part C, 512, c to the 21st, d to the 15th. Part D, 2a to the 4th. Part E, x squared y to the 5th over z squared. And part F, x plus 1 over 3 times x minus 7 to the 5th. Okay, let's take a look at this first one. 2x squared cubed 3x squared. Just think about the meaning of this first cube. That just means that we have 2x squared times 2x squared times 2x squared. 3 factors times 3x squared, so there's a 3x times a 3x. Now the commutative and associative properties of multiplication tell us we can just multiply these numbers 2 times 2 times 2 times 3 times 3. Let's see, that's 8 times 9 is 72. And then we have x squared, x squared, x squared, xx. We can just count up how many x's we have. These will be x to the 4th, then x to the 6th, x to the 7th, x to the 8th. There's one way to think about that. Let's think about another one. You may remember this rule. A times b to the n is a to the n times b to the n. That's a theorem. We could prove that. So, how does that apply here? Well, notice that we have a cube here, so we can rewrite this as 2 cubed times x squared cubed. Then here there's a square. We can rewrite this as 3 squared times x squared. Next, we can just simplify this. 2 cubed is 8. And here we need another rule. This is the rule that a to the b, let's use x, a to the x to the y is equal to a raised to x times y. So here, this is 2 times 3 is x to the 6th. Times 3 squared is 9, and x squared is just x squared. And now, I actually used another rule earlier. I should probably write this one down too, that we're going to use next. If we have, say, a to the n times a to the m, we can simply add those exponents, a to the n plus m. So right here, x to the 6th times x squared, that will give us x to the 8th. And 8 times 9, 72. Part B, we can pretty much use the same rules. This is a squared to the 4th times b to the 4th times a to the 5th times b cubed to the 5th. A to the 8th times b to the 4th times a to the 5th times b to the 15th. Hope you can see I'm just using combination of this rule and this rule. And then all these are multiplied together, so a to the 8th times a to the 5th, we can use this rule, and that's a to the 13th times b to the 19th. See, here we can just again use the same rule, that top rule. So each of these can get raised to the 6th power, 2 to the 6th times c cubed to the 6th times d squared to the 6th. Then each of these gets raised to the third power, 2 cubed times c cubed times d cubed. Then 2 to the 6th, 64. C cubed to the 6th is 3 times 6, 18. C to the 18th. This is d to the 12th. 2 cubed is 8. And we have still a c cubed and a d cubed. Now we can multiply the 64 times the 8 and get 512. C to the 18th times c cubed, that's c to the 21st. D to the 12th times d cubed is d to the 15th. Part D. Let's say here we can just think about each of these, just dividing this up as 14 over 7 times a to the 5th over a times p squared over p squared. 14 over 7 is just 2. We can think about this a lot of ways. One way you could do it is to use this rule, a to the m over a to the n is a to the m minus n. So a to the 5th over a to the 1st is a to the 5 minus 1 the 4th. You could also think about it as you have 5 a's multiplied together on top. This is the product notation. Divided by 1a. A divided by a is 1. These will cancel and you'll have 4 left over. Then over here, p squared times p squared, or p squared over p squared is 1. So we have 2a to the 4th. So using that subtraction rule that I just mentioned, this one is x to the 4 minus 2, or x squared, times y to the 5th, times z to the negative 2. And we were asked not to use negative exponents. Now, one more rule: anytime you have a negative exponent, it simply means to make it a fraction like so. So that z to the negative 2 is really 1 over z squared. We can just put the z squared in the denominator. Over here, we have 5 over 15th, which is a third. X plus 1 cubed over x plus 1 squared. That's x plus 1, 3 minus 2, again using this rule right here. That x plus 1, of course, is just some number. And then x minus 7 to the 4th over x minus 7 to the 9th. That's x minus 7 to the negative 5th. We can rewrite this as x plus 1 over 3 times x minus 7 to the 5th.